Every OLED screen that lights up your phone or television is the result of almost surgical precision, comparable to some of humanity's greatest technological challenges. Billions in investment, decades of research, and the most delicate materials in the world come together to create vibrant colors that have transformed the way we look at a display. But how are these feats of engineering actually made? The ones we now carry in our pockets or enjoy in our living rooms? To find out, we head to the factories of South Korea and China, true fortresses of innovation, where technology and human ingenuity merge to bring OLED screens to life. It all begins with the substrate, the base canvas of the screen. For televisions, polished glass is used, a rigid, transparent material that supports large panels, such as 55 or 65 inches. This glass, often produced by specialized companies, can measure several square meters while being less than 1 millimeter thick to keep the panels slim. Smartphones, on the other hand, rely on plastic fibers such as polyimide, which allow flexible, lightweight screens essential for foldable or curved devices. Folding a television doesn't make much sense, which is why glass is ideal for TVs, while plastic opens up new possibilities for mobile devices. Before use, substrates undergo an initial inspection. Robots equipped with high-resolution cameras scan each piece for defects, measuring thickness with lasers capable of detecting variations down to nanometers. If the substrate passes, it moves on to cleaning, a critical process. The panels are submerged in ultrasonic baths with alcohol or aqueous detergents to remove dust, grease, and other impurities. For glass, mild acids are used to strip away oxides and metallic contaminants. The substrates are then dried in laminar airflow chambers, preventing recontamination. Think of it as preparing a canvas for painting. Any imperfection could ruin the final result. Once cleaned, the substrates are polished with fine abrasive solutions that eliminate micro-imperfections, leaving a surface as smooth as a mirror. In the case of smartphones, an anti-reflective coating may also be applied to improve visibility under sunlight. But how can one ensure this surface is flawless? Optical sensors measure reflectivity and roughness, rejecting any piece that deviates by more than 10 nanometers. This step is critical since poor adhesion could compromise later layers. With the substrate ready, the next stage is applying the electrodes, the conductors that allow electricity to flow. The anode, made of indium tin oxide, is deposited first for its transparency and conductivity. The most common method is vacuum evaporation, where the material is heated in a sealed chamber until it vaporizes and coats the substrate evenly. For the cathode, metals such as aluminum or silver are used, chosen for their high conductivity and reflectivity. In smartphone displays, where energy efficiency is crucial, spin coating is often used. The substrate spins at high speed while a liquid solution is applied, creating a uniform layer. For televisions, vacuum evaporation is more common due to the larger panel size. An emerging technology is inkjet printing, which deposits materials with micrometric precision, reducing cost and waste. Once the electrodes are applied, their conductivity is tested using probes that measure electrical resistance. A poor connection could impact brightness or performance, so this check is essential. Think of the OLED screen as a multi-layered sandwich. The substrate is the base, the electrodes are the conductive layers, and next comes the organic material, the filling that brings the screen to life. These layers are the heart of OLED technology, responsible for emitting light. They include the emissive layer, where organic compounds are electrically excited to produce photons, and the transport layers, which guide electrons and holes toward the emitter. Depending on the desired color, red, green, or blue, different organic materials are used. The main method for applying these layers is vacuum evaporation with a fine metal mask, essentially a stencil with precise openings that allow the colors to be deposited in exact patterns. The material is heated to about 300 degrees Celsius in an extreme vacuum, and particles adhere only where the mask allows. This process is repeated for each color, with alignment so precise that an error of just 1 micron could result in visible defects such as uneven colors. For smartphones, especially flexible displays like OLED, inkjet printing is often used, depositing minuscule drops of soluble materials, much like an office printer but on a nanometric scale. This reduces material waste from 90% down to 10% and is more scalable for large panels such as QD-OLED televisions. In TVs, the challenge is greater due to the size. Substrates, which can be up to 2.5 meters wide, require massive masks and perfect alignment to avoid defective pixels. After deposition, the panels undergo thermal treatment in inert atmosphere ovens, which remove residual solvents and solidify the layers. Finally, optical tests verify transparency and uniformity using LED lights and specialized cameras. Did you know that every pixel in an OLED display emits its own light with no need for backlighting? This allows for perfect blacks, since a pixel that's turned off is completely dark, unlike LCD panels, where light always leaks through. This is what makes OLED images so striking, with deep contrasts and vibrant colors. The next step is encapsulation, an invisible armor that protects the organic layers of the screen from their greatest enemies, oxygen and moisture. If either were to get inside, the screen's lifespan would be drastically shortened. In smartphones, ultra-thin encapsulation is used, built from alternating layers of inorganic and organic materials applied with injection or evaporation techniques. This ensures strong protection while maintaining the flexibility needed for foldable or curved models. In televisions, however, more rigid encapsulation is preferred, often made of glass or hybrid films, ideal for large surfaces that require uniformity. To guarantee perfection, interferometry sensors measure the thickness of each layer with nanometric precision, ensuring a hermetic seal. Once completed, the panels are cut into different sizes, small compact pieces for phones and much larger ones for TVs. Before being integrated into final devices, each screen undergoes rigorous testing, like an athlete in training. They are dropped from different heights onto hard surfaces such as concrete or wood, subjected to extreme pressure, and flexed repeatedly, especially in the case of foldable phones. They also go through electrical tests, activating every pixel to measure brightness and power consumption, as well as optical tests to check viewing angles, sharpness, and color saturation. For televisions, the focus is on large-scale image uniformity, while in phones, the challenge is durability under constant use and mobility. Finally, once they pass all tests, the screens are assembled directly into the chassis of smartphones and televisions. In phones, the panels are integrated with touch sensors and sealed into the frame, ready to respond to every touch. In TVs, they are mounted to the main structure, along with control circuits and auxiliary backlighting, ensuring the entire surface displays a continuous, flawless image. The result is an OLED screen capable of delivering intense colors, deep contrast, and wide viewing angles. In smartphones, it enables flexible and innovative designs, while in televisions, it turns any movie or video game into an immersive visual experience. But the story doesn't end here. From this very technology comes an evolution that conquered the mobile industry. AMOLED displays. Their impact has been so great that today the global market exceeds $50 billion, with projections showing that figure tripling in the coming years. It's no coincidence. They combine OLED image quality with an active matrix of transistors, which allows for more precise control and greater flexibility, a breakthrough that completely reshaped the smartphone world. So how are these displays, which now dominate nearly 80% of phones worldwide, actually made? To find out, we move to South Korea, the global epicenter of AMOLED production. First, let's be clear about what an AMOLED screen is. The acronym stands for Active Matrix Organic Light-Emitting Diode. The difference compared to an LCD screen is simple. While LCDs require constant backlighting, AMOLEDs light up each pixel independently. The result? True blacks, more vivid colors, and more efficient power consumption. To give you an idea of their impact, in 2023 alone, more than 842 million small and medium-sized AMOLED panels were shipped, the majority for smartphones. Samsung remains the leader with 56% of the market. And we're not talking about small workshops, but massive mega factories. In South Korea, Samsung runs gigantic complexes, and in Chengdu, China, BOE built an $8.8 billion facility for its new production line, plants the size of several football stadiums, staffed by thousands of workers. Engineers working alongside precision robots are the ones behind the AMOLED displays we use in nearly all our devices today. Step inside one of these next-generation factories, and you'll find more than just grey industrial buildings. They are high-tech fortresses. Inside, clean rooms rated at Class 100 or higher filter the air non-stop with HEPA systems capable of removing particles smaller than 1,000th of a millimetre, far finer than a human hair. Why such an obsession with dust? Because a single particle can ruin the delicate materials of the display, leading to dead pixels or brightness failures. That's why everything inside is tightly controlled. White LED lighting to avoid interference, workers fully covered in sterile suits moving like astronauts on a mission, and a constant background of fans and sensors monitoring temperature, humidity, and pressure every second. These plants never stop. They run 24/7, producing up to 100,000 panels per month per line. Did you know an AMOLED screen can bend more than 200,000 times without breaking? That's equivalent to opening and closing a foldable phone about 100 times a day for 5 years. All with a panel just 0.3 millimeters thick. Production starts with the substrate, the foundation of the display. While OLED TVs usually rely on rigid glass, smartphones use polyamide, a flexible, heat-resistant plastic that enables curved and foldable designs. This material can withstand up to 400 degrees Celsius while bending without cracking, making foldables possible. Before use, the substrate undergoes a thorough cleaning process. It's submerged in ultrasonic baths filled with isopropyl alcohol and specialized detergents, vibrating at low but steady frequencies to remove grease, dust, and microscopic impurities. After this bath, the substrate can't simply be air-dried like a glass cup. Instead, it's placed inside laminar flow chambers, vertical streams of ultra-pure air that prevent recontamination. Then comes polishing with fine abrasives such as cerium oxide, leaving the surface as smooth as a mirror. How smooth? Laser sensors verify variations don't exceed 10 nanometers. In some cases, an anti-reflective coating of silicon oxide or titanium oxide is added. This reduces reflections by up to 50%, making it easier to read your screen under direct sunlight without squinting. While this treatment takes just a few minutes per substrate sheet, large-scale lines handle plates up to 1.5 meters across, each later cut into dozens of 6-inch screens. Now comes a crucial step before adding electrodes, building the TFT backplane, thin film transistor. This is what makes an AMOLED active. Unlike passive matrix OLEDs, here each pixel has its own transistor controlling the current. Think of it as the skeleton of a smart building. The process is complex. Layers of semiconductors such as indium gallium zinc oxide are deposited onto the substrate using chemical vapor deposition at temperatures between 200 and 300 degrees Celsius. Then comes photolithography. A photosensitive resin is applied, exposed to ultraviolet light through masks with microscopic patterns just 1 micron wide and etched with acids to shape the transistors. This cycle repeats 7 or 8 times, forming a matrix with millions of backplane elements in every screen. To put it in perspective, a full HD display with 1920 by 1080 resolution has more than 2 million pixels, and each one needs at least a transistor. Samsung uses low-temperature polysilicon technology, which allows faster electron mobility, enabling refresh rates of up to 120 Hz. That means fluid transitions and instant touch response. This step is not a minor detail. It represents 30 to 40% of total manufacturing costs. For a smartphone, that equals around $50 to $100 per screen when mass-produced. With the substrate and TFT backplane ready, it's time for the electrodes, the wires that carry electricity through the display. First comes the anode, made of indium tin oxide. It's transparent, transmitting about 90% of light, yet conductive. It's deposited using vacuum evaporation, heating the material to about 2000 degrees Celsius until it adheres evenly in layers just 100 to 200 nanometers thick. The cathode, on the other hand, uses metals like aluminum or magnesium-silver alloys, also deposited in a similar way. But the most innovative technology is inkjet printing, which places 20 picoliter droplets with 5-micron precision, cutting waste by about 30%. Thanks to this, global AMOLED production grows by 11% each year. Next come quick tests. Probes measure electrical resistance, ensuring less than 10 ohms per square centimeter. If it fails here, some pixels could remain dark or shine unevenly, ruining up to 5 to 10% of panels. In AMOLED displays, the electrodes may carry the electricity, but the true stars are the organic layers that generate light and color. This is the heart of AMOLED. Organic compounds that emit light when current passes through, using materials like AlK3 for green or phthalocyanine derivatives for blue. These layers include the emissive layer, where electrons and holes recombine to create photons, and the transport layers that guide them. Depositing these layers is extremely delicate. The main method is vacuum evaporation with fine metal masks, perforated with holes just 20 to 50 microns wide to position red, green, and blue precisely. Each pixel becomes its own light source, which is why AMOLEDs don't need backlighting. By turning off individual pixels, they achieve perfect blacks and can save up to 40% battery power when displaying dark themes. After the organic layers are deposited, the panels go into ovens at 150 degrees Celsius in a nitrogen atmosphere. This removes residual solvents and hardens the layers, shielding them from oxygen, which would otherwise cut their lifespan in half. Next comes encapsulation, a barrier against oxygen and moisture created using thin film encapsulation. Alternating organic and inorganic layers form a flexible sandwich, just 5 to 10 microns thick. Sensors verify that permeability is near zero, crucial for foldables that must survive hundreds of thousands of bends. Finally, the panels are cut and tested. Mother panels are laser cut into sizes from 5 to 7 inches, producing up to 100 screens per sheet. They are subjected to drop tests, pressure tests, and flex tests simulating real-world use. Brightness, power consumption, and viewing angles are measured. All of this ensures AMOLEDs last as long as possible, although their optimal lifespan is typically 2 to 3 years compared to about 7 for LCDs. The final result, displays with infinite contrast, vivid colors, and flexibility, perfect for premium devices. Yes, they cost about 30% more than an LCD, but the quality and experience fully justify it. And that's how OLED and AMOLED displays are made. Tell me, what did you think of these processes? Share your thoughts in the comments. If you enjoyed the video, hit the like button and don't forget to subscribe to the channel. In the windows that follow, you'll find more videos that might catch your attention. Go ahead and watch one. See you next time.